Now let's talk about how to do the training of a neural network in practice. What are the challenges and how to get the things done practically. Let's begin. So this is the agenda. I will be discussing about the optimization, the loss functions, setting the learning rate, adaptive learning rate, gradient descent algorithms, mini batches, SGD, underfitting and overfitting, dropout, early stopping. So all these things will be discussed in this video. Now, optimization. How does optimization help us? Now, training a neural network is very difficult. It is published in this research paper also, you can read it. But the basic understanding says that it's not that easy to reach this point. This bottom point is not that easy to reach. If you start here, you might get stuck here, or you get stuck here, or you get stuck here. If you start from this side, you might get stuck here. You might get stuck this side, or maybe here, or maybe on these sides. It is quite difficult to reach at this bottom point, right? Now, understanding this thing that to reach this bottom point we have to do some computation, and there are various methods. I will be telling the names also. You can go and search about them later on, but this is not such easy task to do just by simply dropping the value, and you might get stuck into this local minima. This is called local minimas, getting stuck anywhere and not here except this point. If you get stuck anywhere, all of the values are local minimas mathematically. Okay, moving ahead. Now, loss functions can be difficult to optimize. We have discussed that. And optimization through the gradient descent is solved by this equation: W equal to W minus eta and this JW by W differentiation. So this is this value eta is called the learning rate. We will see what is learning rate and how it works. How can we set this learning rate, right? How can we do that? What are the different factors to decide what is a learning rate, and which value will help you to reach the minimum point, the global minima? So let's say that the initial guess is we are at this point, and we know that we have to reach at this point where the star is. We have to reach this point. Now, how to do this optimization of learning rate? How do we converge it to this point? There are multiple methods. Let's say that you start by decreasing the value one by one, and maybe you are doing it in a gradient way, and you are decreasing the value too slow, that your training will take a lot of time, and you will maybe reach in eternity at this point if you move at this pace. You can clearly see that the distance is decreasing by approximately half, and you might never reach at this point by decreasing your step size too frequently. So what are the other methods? Let's say you are doing overshooting, you are becoming unstable, you are taking big steps. So if you take a very small step, that's also wrong. If you take big steps, you might hit the next mountain, and then maybe the other one, and you might get reflected, or maybe you reach somewhere else. So you might become unstable, and you are of no use. You cannot reach the minimum point. Now, what is the other method? We have to converge smoothly. We have to avoid the local minima. So we take steps, but initially we take a big step, and then we move slowly, and moving very slowly we will be reaching the minimum point. So this is a theoretical process, but now you have to look at it from the practical side. Okay, let's say how to deal with this. Try lots of different learning rates. You have to pick the learning rate which is just right. You have to reach that bottom point of your learning of your loss function. You have to reach the bottommost point. It has to be just right value, right? You can do it by hit and trial, or maybe try different learning rates. It is very tiring task to do it manually. Okay, the other method is you have to design an adaptive learning rate that adapts to the landscape, the way we saw in the last slides. So we were taking big step earlier, and then we moved gradually, slowly, and we converged to that point, which was the minimum point. So that was the smarter way to do it, adaptive learning rate. So this is how adaptive learning rate works. Learning rates are no longer fixed. We cannot fix it. We should not fix it. We should change our learning rates over time. It can be made larger or smaller, depending on how large gradient is, how fast learning is, right, size of particular weights. So all the different aspects have to be taken care of for deciding the learning rate and for making it adaptive. Now there are multiple algorithms, there are multiple optimization algorithms. SGD is stochastic gradient descent. Adam optimizer is another optimizer. ADA delta, ADA grad, RMS prop. So these are the different research papers who are talking about all kinds of algorithms. One thing is very surprising here. This SGD, stochastic gradient descent, was given in a research paper from 1952. So this concept came very early mathematically. And then Adam optimizer came in 2014. RMS prop did not get published in the research paper. You are not seeing a research paper here. You are not seeing any reference here. Why? Because this was developed during the recording of a Coursera machine learning uh, lectures. So one of the professor was teaching the concept, and they accidentally found this method, and later on they gave this name of root mean square propagation, RMS prop. So this is not published in any research paper, but this is also very widely used, and it has been implemented by Google in this TensorFlow implementation under the optimizers RMS prop. Okay, so Adam optimizer, Adam is a collection of SGD and the RMS prop. So Adam optimizer has multiple hyperparameters also, beta 1, beta 2, and the epsilon, so the learning rate. So all these things are affecting Adam optimizer. Beta 1 is the momentum of SGD, beta 2 is the momentum of RMS prop, the epsilon is for not hitting the infinity for solving the value in the formulas. So if you go into the depth of Adam optimizer, you will see the formula and you will understand what I'm talking about. So beta 1 is having a default value of 0.9 and beta 2 has a default value of 0.999. So just go and read these research papers. These are very interesting research papers actually. Why I'm focusing on this slide more than the others? Because optimizers are one of the most important aspect of getting your answer right in a prediction. Optimizers are helping us reaching that minimum loss function, minimum loss value. We are reaching our prediction to the very near of prediction, maybe 100% accuracy through the optimizers only. So this is a very important slide. You have to go into depth. Okay, moving ahead. So putting it all together, you can solve this by importing TensorFlow STF, and then model can be defined as a sequential model, multiple dense layers can be added here, and then the optimizer TF, Keras optimizer, SGD, stochastic gradient descent. The default values are taken for the SGD if you are not giving the hyperparameters within this bracket. Then while true, forward pass through the network, prediction is equal to model X. So all these things you can try and understand and implement for yourself. Okay, moving ahead now. What are the mini batches? So let's come back to the gradient descent for the moment. This computing gradient means delta JW by delta W, which we have seen earlier. We were trying to reach at the bottom point. It can be very computationally intensive to compute. Obviously, when we are trying to reach the minimum point, it might be that we are hitting a local minima. We are getting stuck at a local minima. We might reach global minima. There is no guarantee, right? So we have to update the weights accordingly based on the learning rate also. So how to do that? Let's say we are trying to do it through stochastic gradient descent. We are not now using only gradient descent, but we have come to use this stochastic gradient descent. So in stochastic gradient descent, you have to do it over the full array of different values. Let's say a pick single data point. Let's say you are not just trying this point, but you are also trying multiple points. Maybe you are coming from this side, maybe you are coming from this side, maybe you are coming from this side. So you are picking different points, the different starting points, and then you are trying to do the same thing, and you are checking through the batches, you are checking it through multiple points, that if you can reach the same point again and again, then it is your final answer, then you are reaching the global minima. If this point is also reaching at this point, if this point is also reaching at this bottom point, if this one is also reaching at a bottom point, then we can say that yes, it is a global minima. I hope you are understanding what I'm trying to say. It's just a way of picking different points. Okay, loop until convergence, but pick single data point I. This I can be different every time. Okay, so easy to compute but very noisy. Obviously now I is changing every time. It can be very noisy, it can be very computationally intensive also. You have to make batches out of it. You are not just picking random points, you have to make a batch of different data points. You are not computing it for the full data set, but let's say that you had this 100 points. You were initially taking different 100 points and computing it every time, and you were reaching the global minima point maximum times, and you were saying that yes, okay, I am reaching the point of lowest loss value. But now the better way is that you pick randomly 10 points out of it rather than the full 100 points. Those 10 points have to be computed for the gradient, and you are reaching the bottom point through only those 10 points instead of all the 100 points. So those 10 points will in a way let you know that if you are hitting the right point, you are reaching the global minima. I hope you get my point of batching. This batch means the small part of values out of the full data set. You are picking a batch randomly, maybe random 10 values out of it. So by using that batch, you will understand and be able to compute the value faster compared to the full data set. Now, mini batches while training. More accurate estimation of gradient, smoother convergence, and allows for larger learning rates. Obviously, when you are testing different points, you have large learning rates, you have a better convergence. So all of those things will be okay. All of those things will be fine because we are trying it for the different points. We are not just using single point to decide and understand or get a bottommost point. Mini batches lead to faster training. It can be parallelized also. So this parallelized computation can be easily done through the GPUs. Why? Let's say that you have 10 million images and you are 10 friends. You are dividing 10 million images into 1 million, 1 million, 1 million into 10 parts, and you are dividing 1 million images among yourself. Okay. Now you all have GPUs. You are computing, let's say person A is computing the loss value over the 1 million images on the first GPU. The second person is doing it for the second GPU for the second million. For the third million images, you are using the third GPU. So all the 10 friends, if start working today, let's say they take 1 week to compute 1 million images. So within 1 week, we have an answer of 10 million images. Why? Because we were processing it parallelly over the 10 PCs, maybe the 10 GPUs for the 10 friends. So this is parallel computing. So this will help you train faster. Now overfitting. What is overfitting? Have you ever heard about it? I hope you have heard about it, but I will try to explain it in a simplified way. So let's say that you are trying to fit a line among these points. See in the left figure, among these points you are trying to fit a straight line. So this is underfitting, right? Underfitting. Why? Because you are not trying to plot according to the different values, but you are just randomly trying to fit in a line and try to predict the results. What is the drawback of this function? This underfitting technique will lead to more errors. Your predictions will not be right. Model does not have the capacity to fully learn the data. So it might be that your model is not performing well because it does not have the capacity to understand the complexities behind it, because you are not using nonlinearity, you are just using a linear function, right? This is problem of biasness. And what is variance or overfitting? Variance or overfitting means you are going to each and every point. You are trying your best to touch every point and try to learn each and everything, that whatever comes I will be able to predict, right. So it is too complex, it has extra parameters and does not generalize well. Why does not generalize well? Because you are trying to cram your values, right? You are trying to cram all the points, and by cramming you can only answer those things which you have learned. But if the question is not, if the data point is not inside the space of training, if it is out of the, maybe it is out of syllabus, you can say, maybe it is from the testing data set or a validation data set, so that point will not be able to predict in a way, the way it is predicting the overfitted model, because overfitting will also take more time. Okay, you are improving, you are taking lot of parameters. So let's say you are solving this equation. So this is a linear equation, it is very easy to compute and it will not take much time to do the computation for the linear equation. But when you are adding a lot of curves into the equation, a lot of parameters will get added. Let's say on every curve you are adding different parameters. So this is parameter 1 2 3 4 5 6 7 8 9 10. So let's say there are 10 parameters. Your equation will be having x raised to power 10 plus x raised to power 9 plus x raised to power 8 up to x plus the bias value, the x naught. So all of those things will lead to a very complex equation, and it will take a lot of time to solve, and it will not answer, it will not give it, if the, it will not give the prediction right. The ideal fit is that you add a bit of non-linearity and you will be able to answer the things better. So this is an ideal fit. Now I want to add one more concept to it, human level performance. So let's see an example of cat versus dog classification. Now given a set of cats and dogs images, a human can give a very high accuracy result. You have to just say if the image is having a cat or a dog. Only if you are not able to predict or understand the breed of a dog or a cat, you might do some error. So we are saying that you will get 99.8% accuracy in telling if it is a dog or a cat. But if you are saying that your model is being trained, the training set accuracy is 93%. I hope that you understand this decision. Train, test and validation dataset. So all these three datasets will be worked upon. So your training set accuracy is 93% and the test and validation set accuracy is 80%. So on the testing dataset your accuracy is 80%, your training dataset is saying 93%, and the human level accuracy is 99.8%. Now if we see the difference between 99 and 93, the difference is 6.8 here. This A minus B, human level accuracy minus the training set accuracy, this is called the avoidable bias. This is a bias problem, right? This is a bias problem. Why? Because you are not able to perform as per the human level accuracy. You are not even reaching near to it. So this is kind of, you are not performing well. The model should perform well, it should train better, it will attain the human level accuracy. During the training it has to, you have to do a ideal fit, not the very complex one, not the overfitting, but yes, you have to train well. Now test accuracy 80%. Why? Because you might have trained it more and you have hit overfitting, and that's why you are unable to perform well and you are getting 80% accuracy. So the difference between this training accuracy was 93%, testing should have been near to 90, 91, 92, something like that, but you are getting 80%. Now because the difference is of 13%, so this is called variance or an overfitting problem. So these were the three concepts that I wanted to talk about: the bias, the variance and the human level performance. Okay, now regularization. What is it? Technique that constrains our optimization problem to discourage complex models. Now we have seen earlier that overfitting will lead to more time of training and not a good accuracy while the testing. So there will be multiple issues if your model is overfitting. Now there is a way to reduce that overfitting, and regularization has to be done. You have to regularize all the learning. Now why do we need to do it? Because the generalization will be better. Testing dataset is the unseen data, right? Testing dataset has not been given to the model while the training was being done. So improve the generalization of our model for the unseen data. Regulation is important. One of the technique, very famous one, is dropout. The dropout method was given by Mr. Srivastav in 2014 in a research paper. You can go and search about dropouts, and you will see the you will find the research paper which one is doing this. So during training, randomly set some activations to 0. Let's say that for the first layer you are dropping out 50% of the data, and for the second one you are dropping out 25% of the data. So dropout means making your activation 0. So we are dropping 50% of the layer. So this 1 1 and 1 3 are being dropped. They are not being connected now. So you can see that there are 3 out of 8 neurons in these 2 fully connected layers which have been dropped out, which will lead to less connections. So uh, tf.keras.layers.dropout p equal to 0.5. Now this command has to be used after, let's say, this dense layer. So just imagine the dense layer has been defined at this point just before the dropout, and then you are saying 50% has to be dropped. So let's say you have these dense bracket 4, so all of those 4 nodes have been defined, and then you are dropping out zero point 0.5. So p equal to 0.5 means 50% chance is there that the node will be surviving for passing the activation value. So after dropping out, the connections are less, so that will make your network not to rely on any one node. You are not relying on a particular node. You are not relying on this 1 comma 2. It might change on the next loop. So let's say that z11 and 13 were activated in the next iteration, and you are dropping out 1 comma 2 and 1 comma 4. So you are not relying on a particular node. You are giving equal weightage to each node, and based on that, regularization can be done. Overfitting will not happen. So early stopping is also one of the method to reduce the overfitting. Early stopping means, let's say that you are doing training and testing, and while training you were getting less error, and testing was giving a bit more error, but over time you reach this point that training was reaching at the bottom point, but the testing was again error was getting a bigger number, right? So this was, I think this was the right point that you should have stopped your training, and based on that you would say that yes, it is the best testing loss we can achieve, because uh, before or after this point you are getting more error, more loss at the testing part. So let's stop here, and when we stop here, on the left side was underfitting. If we had stopped earlier, it was leading to underfitting. If we are stopping after this point, you will lead to overfitting. So this is the ideal point, so you should stop here. This is early stopping. Thank you.